Okay, so far we've been looking at derivatives as far as abstract on the Cartesian plane, change in y over change in x, slope of the tangent line. Derivatives have many applications. One of the applications or types of problems in calculus with derivatives are called related rates. Okay, and the derivative itself is a rate. The slope is a rate, change in y over change in x. Okay, it's a rate. So we're going to look at a problem where there's an oil tanker that is leaking oil in the ocean. And the problem says that oil spilled from a ruptured tanker spreads in a circle whose area increases at a constant rate of 6 square miles per hour. How fast is the radius of the spill increasing when the area is 9 square miles? Okay, so they've given us some information here. And the first one they said constant rate. So they said the area increases at a constant rate. So area per time, dA dt. And when we're looking at derivatives this way, if I have dA dt, derivative of the area with respect to time, I need a rate in terms of area per time. Okay, and they told us in this, they gave us that it was 6 square miles, so 6 miles squared per hour. Okay? So there is the rate of change of the area with respect to time. And again, look at the units. Miles squared is area, hours is time. Okay, and again, if you're doing related rates and you're setting up a problem, you want all of the units to be the same. You can't have time in seconds in one part and hours in another part, just like if you were in a science class. You'd want everything to be in terms of the same linear units, and in this case, because it's a rate, we're talking about time. The time units need to be the same as well. Okay, so then they say, how fast is the radius of the spill increasing when the area is 9 miles squared? Okay, so we need the area formula for a circle. Area equals pi r squared. Remember, pi is a constant. Okay, now what we're going to look at is we're going to take the derivative of this area function for a circle, and because it's a related rate, we've got another variable there, time. You can kind of think of it like a parametric equation. Time is a hidden parameter here. So when we take this derivative, I'm going to take the derivative of everything with respect to t. So I'm taking the derivative of the area with respect to time, and I'm going to take the derivative of pi r squared with respect to time as well. Now, the dA dt is just that, dA dt. Now the right side, remember, pi is acting as a coefficient in front of r squared. It's a real number value. So when I take this derivative, it's 2 pi r, that should sound familiar, but 2 pi r for the derivative of the area. But again, I need it with respect to time, so I've got dr dt. Okay, so we identified the equation or the relationship that we need in this case, which is the area formula for a circle, pi r squared. We took the derivative with respect to time. So notice here, we have one variable, it's a rate, dA dt. We've got another variable, the r, which is the radius, and then we also have the third variable, how the radius is changing with respect to time. Okay, so they told us, they said, how fast is the radius of the spill increasing when the area is 9 miles squared? So basically what they have given us is information at an instant. So at an instant in time, we have the area of the spill is 9 miles squared. So 9 equals pi r squared. Okay, so that means then we need to find out what the radius was when we had the value of 9 here. Okay, so that tells us then what? We've got to solve for r here, okay, which means that r squared equals 9 divided by pi. So r is going to equal 3 over the square root of pi. Okay, so at an instant, when the area of the spill is 9 square miles, we needed to find the r value, which is 3 divided by the square root of pi, and we could find that, we could rationalize that value for r, but it's not necessary because we're going to plug in. Okay, so to start us off, they gave us dA dt, how the area is changing. We've got that as one variable. We also just found r, which was a value at an instant that they gave us. So it was r is equal to 3 over root pi. So I can plug in for r, and then we're going to solve for dr dt, because that's what the question asked. How is the radius changing with respect to time at a specific instant when our area was 9 square miles? Okay, so let's plug in our values. And again, I could label the units. This would be, r would be 3 divided by root pi miles. So it's, and so, but again, it's not necessary if everything kind of lines up here. So my dA dt they gave us was 6. Okay, and that has to equal 2 pi times r. Now r I'm going to plug in as 3 over root pi. Okay, and then the dr dt was what we are looking for. And if we had put all of the units in here, when we solve this, we should be able to get something where the units cancel and we're in the correct units, okay, but it would have been cumbersome on the board here. So let's solve for this dr dt. Okay, so first things first, I can see I've got a 6 on the left, I got a 6 on the right, so that means that all those are going to cancel. So I've got 1 equals pi over root pi times dr dt. So again, I'm going to multiply both sides by root pi over pi, not root 11, so root pi over pi. So, and that's a dr dt, not a d pi dt. So that means that dr dt is going to equal the square root of pi divided by pi. Okay, and it's a rate per time. So in this case, it would have been linear unit miles divided by hour for the units. It was already rationalized. We could unrationalize it, okay, and make it 1 over root pi. Okay, but we found dr dt at an instant for this related rate. So first off, they gave us some information. We kind of identified that that was a dA dt because it was changing in square miles per time. I then said, well, let's set up an equation, or what equation I think we're going to need, which is the area formula for a circle. Took that derivative with respect to time, as we always do with related rates. Once we see that, we've got 1, 2, 3 variables. One of the variables they gave us information about. We had to find one more to solve the one variable equation to have only one variable left, so we found the r at an instant. From there, plugged in, and we found dr dt, and again in this case it was the square root of pi divided by pi, and again you could get a calculator out and get a decimal approximation, but that was in miles per hour. That was a dr dt, change in radius per time, and again at that instant.